Good afternoon, everyone. Welcome to today's SANCOLD YPF webinar. I'm your host, Ashley Kutsia, the SANCOLD YPF Chair. Today's session focuses on benchmarking numerical analysis in dam engineering, drawing from insights presented at the 17th SANCOLD Benchmark Workshop. It is my pleasure to introduce today's speaker, Ryan Castles, a professional engineer and structural dam engineer at ARQ. Ryan has over a decade of experience in the structural analysis and dam design of dams, with a strong focus on advanced numerical modeling and finite element analysis. He has worked on a wide range of dam projects internationally, including large concrete and RCC dams under complex loading conditions, such as thermal and seismic effects. He is also the South African representative on SANCOLD Technical Committee A, which focuses on computational aspects of dam analysis and design, and has authored numerous technical papers in this field. Ryan, thank you for presenting today. The floor is yours.
Thank you for that introduction, Ashley. I hope everyone can hear me. Can I get a thumbs up if it's audible, please?
You are audible.
Thanks, Ashley. Okay, I'm going to proceed to share my screen. Let's hope I can get it right as we practiced.
All good.
Okay, cool, 100%. Okay, come on. Okay, can use the arrows, that's fine. Okay, thanks. As Ashley said, I'm Ryan Castles from ARQ Dams. The topic of my webinar, benchmarking numerical analysis of dams, insights from the 17th SANCOLD Benchmark Workshop. Various organizations playing a part here. It's hosted by SANCOLD, which is the Bulgarian National Committee of Large Dams, a member of SANCOLD, in association with the University of Architecture, Civil Engineering. It's a technical university in Sofia. And also this benchmark workshop was obviously an official SANCOLD event. Okay, quickly going through the presentation structure. I'll start by looking just at the introduction and background for those of you who don't know what a benchmark workshop entails. Run through the objectives and scope of the workshop. Look at the topics that were studied, as well as the various contributors and participants. I'll look at the modeling approaches and results. I'll highlight some of the key findings, and I'll quickly discuss the site visit that they did, which unfortunately I was not there, but the site visit was quite interesting. And looking at some extras as a bonus, and I'll end with a conclusion. So the SANCOLD Technical Committee A is given the duty of looking at computational aspects of analysis and designs of dams. It was the Technical Committee A, which are informally referred to as TCA, who hosted this event. This is the 17th benchmark workshop. It was held at the IEC venue in Sofia, Bulgaria, last year, April 2025. The workshop proceedings were peer-reviewed by 15 reviewers, and the proceedings were published on open access platforms. So basically, it's freely available to anyone who's here listening. Anyone can actually download the proceedings. I've put the link in the slide there as well. And I'm sure if anyone asks, we can find a way to share that later. Just a photo on the right showing the conference setting, and on the left-hand side, a photo of the venue. So the SANCOLD Technical Committee A, as Ashley said, I'm the South African representative there, was formed in 1988 by SANCOLD. The objective and the goal was to verify correct implementation of theory, based on the finite element method in dam engineering. Just to stress the one thing that this is structural analysis, finite element modeling, not necessarily, not computational fluid dynamics, which obviously also a lot of dam engineers use, but that's more in terms of the flow of hydraulic flow and things like this. This is strictly finite element modeling for structures. The benchmark workshop is held every 2 years. I think the first one was in 1991. After that, they normally do capitalization of the findings and publications. And then also there are bulletins released every now and again by Technical Committee A, Bulletin 94, Bulletin of 1994, Bulletin 122, 155, 202, and 206. These bulletins are all basically giving information related to numerical modeling of dams. The chair of the committee is Antonella Frigerio. She's from Italy. And the co-chairs are Russell Gunn, he's a Swiss gentleman, and Gerald Zenz from Austria. There's a photo of me when I attended the benchmark workshop. Antonella, the lady with the black hair, and to her right, Gerald, and to her left, Russell, and obviously you can see me. As I said, the benchmark workshop was hosted by SANCOLD, which is the Bulgarian National Committee of Large Dams. They've been a national member of YPF since 1938. The chairman is also a professor at the UACEG, which is also one of the event organizers. His name is Dimitar Kislyakov. The vice chairman is also Dimitar Popov, and the honorary chairman is Dimitar Chashev. So I think if you live in Bulgaria, there's a high probability your name will be Dimitar. A photo on the left is showing the building at the university. The benchmark workshop took place in Sofia, Bulgaria, which is the capital of Bulgaria. It's in Eastern Europe. Interesting enough, it's one of the oldest European cities. It's been inhabited for 7,000 years. It's actually older than Rome, Paris, and London. The city is located directly next to the Vitosha mountain in the Balkans mountain range, so ideal setting for dams. Bulgarians love yogurt, and they swear by getting longevity from it. And they also enjoy to drink rakia, which is a fruit brandy. They drink socially, and they also swear by it as a cold remedy. Some of the photos in the middle here, you can see the city skyline, and with the beautiful mountains in the background. A map just showing where Bulgaria is and the city, the capital, Sofia. On the right-hand side, a famous photograph of the Alexander Nevsky Cathedral. And then, let's go to the next slide. Sofia is also rich in culture and eclectic architecture. You can see all the beautiful colors of the different buildings. The city is also located above natural hot springs, so when you walk around in the city, you'll see various points where people are able to freely collect heated spring water from taps. And one of the things that Henry John joked with me before I went is that in Sofia there's a bit of a thing about how is the name of the city pronounced. Is it Sofia or Sofia? I can't remember which is the correct way, but I know some of the locals get irritated by the tourists. I think the correct pronunciation is Sofia, but a lot of people say Sofia. It's just an interesting fact. Okay, let's get to the dam. So, as I said, Bulgaria is a very mountainous area, which is perfect conditions for dam building. Some of the notable large dams in Bulgaria, the Vacha Dam, 144-meter high concrete gravity dam. On the left photo over here, the Student Kladenets Dam in the middle here, which is a 68-meter high concrete gravity dam. The Kardzali Dam, top right corner, 103-meter high concrete arch dam, and the Tsankov Kamak Dam, 130-meter high concrete arch dam. So you can see there's really some cool dams in the area there. The dam on the bottom right actually features in the benchmark workshop studies. So we'll unpack that dam a little bit more. So how would one define a numerical modeling benchmark workshop? It's an international gathering of numerical modeling experts in structural dam engineering. The contributors undertake predefined numerical analysis studies of selected dams. The model parameters, the assumptions, and the analysis considerations are normally to a large extent standardized. This is to try and pick up if there are differences in the outputs, that it's not necessary having different modeling assumptions, but where these differences, what they arise from, what causes them. Contributors undertake these studies using their preferred numerical modeling software and processes. And of course, there are some selective analysis assumptions, these normally being those of current interest, where I'd say the goal or the objective is to actually find out how these different assumptions impact the structural response or the analysis results. And just a few nice photographs taken from some of the proceedings. Some images of the mesh there. You can see the mesh of the dam. So yeah, this is the, as I mentioned, let's get the name right, the SANCOLD Dam, which you can see in the mesh over here, and the photograph on the bottom right. So the aim and objectives of a numerical modeling benchmark workshop to compare study outcomes and results between contributors and FEA software packages, to identify and explain significant differences between the outputs and results. It's also very useful to provide analysis reference points for newly developed software or newcomers or participants. For instance, if you're a dam engineer and you need to venture into numerical modeling, you've got a complex problem, you want to buy a new software package, how do you test it? You can use the benchmark proceedings for that. And as I said, there have been various benchmark workshops before this one. Other objectives: to share the knowledge and interact or network with fellow professionals. That is also the main purpose of this webinar. It's for me to share what I learned at the workshop with SANCOLD members, and to advance the knowledge and experience of the DAMS FEA community. So the workshop structure and content. Basically, prescribed FEA studies are formulated by the TCA, which is Technical Committee A, defining analysis requirements and reportable results. The formulation is released online in advance together with workshop dates and a venue. Interested contributors can undertake these studies using their preferred numerical modeling software. To partake in a benchmark analysis in a workshop, you don't need to be a member of ICOL or SANCOLD. It's free for anyone to participate. The formulations are normally freely uploaded or available on the ICOL website, or the ICOL website will actually refer to the specific website set up for the benchmark workshop. The analysis results derived by contributors are submitted to the organizers. So once all the various contributors do their work, they submit it. The organizers assimilate, evaluate, and summarize the findings and make comparisons between the outputs. And the organizers and the contributors present the findings in a conference-style workshop. And eventually the proceedings are published. Just for interest's sake, for this workshop, there were 13 contributors from 9 countries, and there were 50 plus workshop participants. So you can either be a contributor and a participant. If you're a contributor, you actually take part in the exercises, or you can just be a participant. You can just pay the fee and attend the workshop and learn from it. The contributor organization type, there were 5 universities involved, 9 engineering firms, and 1 software developer. And actually 8 FEM software packages were used, which is quite nice. So it's quite a good spread. Some of the more well-known software packages, Abacus, you can see the blue, 4 people used Abacus. ANSYS in the green, 3 people used ANSYS. LS Diana, 3 in the orange, 3 people used that. So yeah, you can see there's quite a good representation there. Unfortunately, I wasn't able to contribute using Midas. I would have loved to. I was quite busy at the time, but I definitely intend to contribute to the next benchmark workshop, and to see where the Midas FEA Index software stacks up with the rest. That'll be very interesting. You can see in this table just the various authors and the countries that they come from: USA, France, Italy, so it's all over the world. even New Zealand, even Russia. Okay, so the workshop had 3 themes. Each of these themes is represented by a different type of dam. Theme A was 3D seismic analysis of the SANCOLD concrete arch dam, which I showed you a bit earlier. Theme B looked at the first impoundment of the Plovdivitsky embankment dam, which is an asphalt concrete core rockfill dam. Theme C, calibration and prediction of the rockfill behavior of the 210-meter high Namnagum CFRD dam. That's actually not in Bulgaria. That dam is located in Laos, but the dams for Theme A and Theme B are Bulgarian dams. And then you can see the photographs on the left, the Arch Dam, the middle, the Plovdivtsky Dam, and on the right-hand side, the Namnagum 3. For purposes of this webinar, I'm only going to really look at Theme A. There's quite a lot to unpack, and it would be impossible to do all themes in 1 hour. But yeah, the proceedings are there, and for those who want to look at the embankment dams and the rockfill dams, you're more than welcome to have a look at that. So that SANCOLD Dam, 130-meter high double curvature concrete arch dam, 486-meter crest length, the reservoir capacity of about 100 million cubic meters, spillway capacity of 1,450 cumecs, hydropower capacity of 80 megawatts, a rock mass geology comprising of metamorphized biotite gneisses. Just to compare the size of the SANCOLD Dam, as I said, 130-meter high. In the table, I've got 5 large dams in South Africa: Van der Kloof, Stakfontein, Pongola Poort, Gariep Dam, and Vaal. So you can see that in terms of the height of the structure, the SANCOLD Dam is a really big dam, larger than all our largest dams. But obviously, if you just look at the reservoir capacity, it's not as much as what our dams hold. But yeah, purely from a structural point of view, it's a very large dam, 130-meter high. So theme A, as I mentioned, is the 3D seismic analysis of SANCOLD Dam. The objective and purpose of theme A is to identify and evaluate findings that contribute to the development and better application of advanced methodologies for static and seismic analysis of concrete dams, to compare results from linear and nonlinear analyses, to compare analysis results across different modeling approaches and software, highlighting similarities and discrepancies, as well as to understand the potential for various modeling approaches or software to yield results having quite a broad spectrum at times, and also to allow engineers, researchers, software developers to discuss their solutions to given analysis problems. Here is just 2 images, plots taken from the proceedings. I'll go through the details of these later. Then theme A had 6 case studies, so looking at different loading conditions, and obviously these case studies also had sub-case studies, so you can see there's quite a lot of analyses taking place here for the contributors. Case study A, static analysis, also made up of 3 sub-cases: case study A1, A2, A3. Case study B, modal analysis. Case study C, foundation dynamic analysis. So that's just the analysis of the foundation only without the dam, to look at the propagation of the seismic input from the foundation base up to the surface. Case D, linear dynamic analysis of the dam and foundation. So now you're including the dam and the foundation. Case E, nonlinear dynamic analysis. So basically starting to include non-linear material modeling in the dam. And case F is a linear massless foundation analysis. There's often a lot of debate between a mass foundation and a massless foundation seismic analysis. So obviously both cases were looked at. As I said, some of the analysis cases were deemed mandatory. So in order to actually qualify as a contributor, you would have to do all the mandatory analysis cases, while others were optional. The optional ones sometimes being a lot more complex and technical and requiring a lot more time And not, as we know, these things can take long, and they don't. Not everyone has the time to do all of them. On the table on the right-hand side, the contributors is divided into 30 numbers. So it's assigned random numbers just to not to expose the various participants in terms of their name or their organization. But you get contributors P1 to P13, the FEM code that they used, and just showing which of the case studies they actually undertook under theme A. Case study A1 is a monolithic linear analysis of the dam. Case study A2, a nonlinear analysis, adopting nonlinearities at the contraction joints between the blocks of the dam, with the intention of getting a stress distribution there. And case A3, nonlinear analysis at block interfaces and at the dam foundation contact. Just giving some of the dam and reservoir data that obviously needs to be input for the modeling. The dam crest elevation, 688 meters above sea level. Dam crest length, 468 meters. The crest thickness, base thickness. Don't need to go through all of them. What is applicable is the annual average water level of 679 meters above sea level. That's considered your normal loading conditions for purposes of this analysis. So for static and hydrodynamic loading, this is the number to consider. The dam body details. The dam body is a parabolic arch profile. It contains 300,000 cubic meters of concrete. The dam was constructed with 23 blocks or monoliths, each 20 meters wide. Between the blocks at the contraction joints, 100 millimeter shear keys were constructed to get monolithic behavior across the arch. And obviously the joints were later grouted as well. Here's a nice plan view of the dam arch and showing the setting out of the site, or the setup of the site, the contours, the valley. And on the right-hand side, just a cross-section of the crown or central cantilever, which is basically the tallest or highest part of the dam, which is the deepest portion of the river valley. For contributors who were taking part in the analysis, the mesh of the dam and foundation was actually provided. Again, this is to try and eliminate differences in analysis results from people having different meshes, different element types. So geometry was provided as well, but a mesh of the dam and foundation was provided for the contributors to use in their analyses. The mesh comprised 8-node isoparametric solid brick elements, the dam element size being 4 meters. You can see on the right-hand side the mesh of the dam, very nice, neat mesh, all the element, good aspect ratio, foundation transitionary mesh, 85,000 nodes and 77,000 elements, and the reservoir modeled with acoustic or fluid elements, 22,000 nodes and 19,000 elements. The concrete modeling assumptions, which were given as well to the contributors, the density concrete 2,370 kilograms per meter cubed, Poisson ratio 0.2, static elastic modulus 28 gigapascals, dynamic elastic modulus 34, thermal expansion coefficient 10 e to the minus 6, compressive cube strength 25. So it's all quite standard concrete properties. The foundation modeling assumptions. Density 2,675 kilograms per meter cubed, your Poisson ratios, then your rock mass shear strength, a cohesion of 1.5 MPa and a friction angle of 60. So you can clearly see that's quite high shear strength parameters indicating nice competent rock mass, and a static elastic modulus of 28 and dynamic 34 derived from a shear wave velocity of 2,220 meters per second. The reservoir modeling assumptions, the density of water 1,000 kilograms per meter cubed, pretty standard. Compression wave velocity 1,439 meters per second. The bulk modulus 2.2 gigapascals, and the median type fluid. Okay, so for case study A1, analysis assumptions, monolithic linear static analysis. So not modeling any nonlinearities, not at the contractions, joints, nor at the interface between the dam and foundation. The dam concrete modeled as linear elastic. The loading, hydrostatic, gravity, and drained uplift. And the foundation extends restrained against translation. So it's all quite standard and normal hydrostatic, linear elastic analysis. The required results from contributors, displacement results of the dam at the crown cantilever, which is your central cantilever. You can pretty much see the mesh here and the red points indicating the points along the heights of the central cantilever where displacements were to be extracted. Other required results from the contributors being the minimum and maximum hoop stress on the downstream and upstream face, as well as the minimum and maximum vertical stresses also on the upstream and downstream face of the central cantilever, and then also contour plots of the major principal stresses. Normally these major principal stresses give us an indication of where we can expect tensile stresses to develop in the dam. So taking a first look at the results comparison for case study A1, the plot indicates the radial displacement of the dam towards the downstream, so positive displacement in meters being towards the downstream, and on the y-axis the elevation. So you can see obviously as you go up the height of the dam, the displacement increases towards the crest. Interesting enough, there were, well, okay, first of all, by the different colored curves, you can see the displacement curves for the various contributors, P1 to P13. Interesting, you can see there's sort of two groups of results and then two isolated results that don't correlate with the rest. It was found out later that although it wasn't specified, one group of contributors reset the displacement of the dam under gravity before applying hydrostatic. So in other words, they applied the analysis as a stage construction approach where they placed the dam under gravity, let the dam displace and develop stresses, and then zero the displacements and then place the hydrostatic loading. So that would normally give you a greater displacement because you're only getting the downstream displacement from the hydrostatic loading, whereas if you place the gravity and the hydrostatic loading together at the same time, you'll have less displacement because under gravity the arch dam actually leans a bit towards the upstream side. So the set of curves on the left, obviously being the case of the contributors who applied the gravity and hydrostatic loading simultaneously, and the curves on the right, the light blue, the dark orange, contributors who actually applied the loads at different stages. And the yellow curve, contributor 4, sort of follows the one group towards the base, and then at the crest close to the other group. Apparently they built the dam up under 11 stages, which is obviously, there's good advantages to that, but I don't think it was part of the brief for the study. But normally if you really want to get accurate stress results, it is good to build the dam up. P3 also, the orange curve showing quite a lot of difference between all the rest of the contributors. But generally you can see there's a good correlation between the groups, both based on the assumed loading sequence, apart from P3 really. The stress result comparison on the upstream face. So the contributors were required to give the hoop and vertical stresses. The plot on the left showing the hoop stresses along the height of the dam, negative stresses indicating compression and positive tension. And on the right-hand side plot, the vertical stresses along the crown or central cantilever up the height. Again, negative stresses being compression and positive being tension. Again, generally a good correlation between all the contributors. This time you don't see that big difference between the stages of the loading because it was the displacements that were zeroed, but not the stresses. So if you place the loads at different times, the stresses are quite similar still. On the upstream face of the dam remains in compression along the horizontal arches. The upstream face of the dam also in vertical compression. This is due to the double curvature or the overhang. So That gives you a nice vertical compression in your arch. The only outlier here, again, is contributor 3. But there is a sense of, what's the word I'm looking for, disparity, or there's a difference in stress results at the base of the dam, the vertical stresses, and that's your normal sort of finite element modeling artifact where you have stress concentrations that develop at the heel of the dam. This is due to various modeling artifacts such as reentrant corners and singularities, but basically you can see the rest of the height of the dam, the vertical stresses are all, there's quite a tight fit between all the different contributors, but towards the base you can see that participant or contributor 11, which is the dark blue, actually calculated tensions of close to 4 MPa, where the others calculated vertical tensions ranging from 2 MPa to pretty much 0, and some of them even got, the light blue got vertical compression. So that's always your first sort of anomaly in numerical modeling, is the stresses at the heel or the base between the dam and the foundation. The stress results on the downstream face, so normally you look at the upstream and the downstream face. Again, there's generally a good correlation between all contributors. You can see there's quite a close fit between all the various curves. Again, the stresses remain in compression, basically for horizontal and vertical. Remember, this is the normal loading condition, so it's pretty much equivalent to like a full supply level, and it is an arch dam, so you don't expect tensions to really develop under normal loading conditions. There's also no sign of horizontal bursting stresses. There are minor vertical tensions that form just above sort of mid-height of the dam in this region of about 0.5 MPa. This is just due to the structural propped cantilever effect. So basically you've got a cantilever which is then supported by a spring. So basically the arches provide a stiffness to the cantilever, so you get a little bit of tension developing there, as you would if you had a propped cantilever and a hogging moment. The major principal stress results plots on the upstream face. So generally there's a consistent stress pattern among all 12 contributors. Tensile stresses are confined to the dam foundation interface at the heel. The concentrations due to mesh reentrant corner, as I said, change in stiffness, a singularity effect, the maximum tensions ranging from 1 to 3 MPa. And you can see all the various maximum or major principal stress plots from all the different software packages. I'm sure some of you may be familiar with some of these. There's FLAC 3D and yeah, but obviously you see they all have different user interfaces and they use different contour colors to represent the stresses. It's quite interesting to see that. Case study A2, basically the same as case study A1, except that nonlinear material modeling properties were adopted at the contraction joints between the monoliths. Yeah, so it's basically an explicit joint given a very low tensile strength, or as close to possible to 0. The normal and the shear stiffnesses were given a value of 1 to the 12 pascals per meter. This is all according to the inputs from the organizers. The dam is still attached to the foundation, so you don't have an explicit joint at the dam foundation, only between the actual blocks. And the loading, again, is just hydrostatic, gravity, and uplift. There's a typical material model showing elastic brittle, so you got linear elastic stress strain curve until the point of failure, and you get a large drop in the stiffness. The displacement results comparison. Again, on the plot on the left, these are the radial displacements, positive being towards the downstream. You can see again, or this time there were only 6 contributors, so only 6 contributors went to the nonlinear. There's again 2 distinct groups, those who applied the gravity and hydrostatic loading at the same time, and those who opted to first put gravity loading, 0 the displacement, and then put hydrostatic loading. Again, generally a good correlation. The results between A1 and A2 don't differ drastically. There's small differences, and that is expected because obviously there's not much tension really forming across those contraction joints, as would be the case if this was a seismic analysis, which we'll get to later. But under normal loading conditions, hydrostatic, most of the things stay in compression, most of the stresses. On the right-hand side, here's a plot from A1, which we looked at earlier, and on the left, a plot from A2. So on the right-hand side, just linear elastic, monolithic dam. On the left-hand side, linear elastic concrete, but non-linear modeling between the contraction at the contraction joints. Stress results comparisons on the upstream face. So you got your hoop for axial and vertical stresses of the dam versus elevation. So similar set of results as for in a case study A1. Generally a good correlation. The upstream face of the dam remains in compression along the horizontal arches, and the upstream dam in the vertical compression due to double curvature. What is interesting to note is that on the upstream face at the heel of the dam, you don't get that development of large excessive tensions, which we showed earlier. And this is not, as I said, there's no actual discrete joint model at the dam and foundation, but that tension is obviously actually released then across the expansion and contraction joints. So that's why you don't get any tensions forming over here. Stress results comparison on the downstream face, pretty much similar, good correlation between all the contributors. Case study A3. So this was the most nonlinear case where, again, nonlinearities were modeled at the contraction joints between the monoliths, as well as between the dam and foundation. So if you look at this image, you can see interface elements between the dam blocks and as well at the dam foundation interface, whilst the concrete material property was given also fully nonlinear material model using the concrete damage plasticity model. This is basically where you can input a stress strain curve into your analysis software. Here's just an example of a stress strain curve for your compression, compressive stresses and the tensile stresses. Basically, the first part is linear elastic until it starts to yield a bit, and strain harden until failure, and then strain softening. That's in compression, and in tension looks a bit different. But basically, that allows you to really get a good nonlinear structural response of your dam. The displacement results comparison, very much similar again to the previous ones. This time we only had 5 contributors submitting for case study A3. The results don't differ much between A2 and A3. Once again, there's not a lot of tension under normal loading conditions, so you wouldn't see large differences. Stress results on the upstream face, similar thing, don't need to repeat that. On the downstream face as well, hoop stresses on the left, vertical stresses on the right. So for case A findings, so that's the end of case study A. Stages of hydrostatic loading effects, the displacement of the dam. The displacement of the dam under gravity is normally built out in real life, but it also depends on the impoundment strategy. So is the dam built and impounded at the same time? Like, for instance, at Katse Dam, that's how they did it. Other dams are constructed to crest level and only impounded later. So it all depends on what the construction sequence is. Linear elastic hydrostatic loading of concrete arch dams indicate exaggerated tensions at the heel. I actually did a paper presenting this in 2024 for SANCOLD with my co-author, Dr. Wright. So you can see the stuff that we've been presenting at SANCOLD correlates quite well with what the guys are doing at the benchmark workshop. Use of nonlinear material models allows for redistribution of tensile stresses at the heel and across the joints. If I remember correctly, I think that was for the Olifantspoort project where I presented that. So that's quite a useful feature. using nonlinear material models. What is important is the selection of a nonlinear material model is very critical on how the stresses are redistributed. There's obviously so many different types of models out there. You need to make sure that you select a model that really represents your site conditions and one that's been tried and tested. And yeah, do some V&V analysis just to see what comes out. There's also various nonlinear models for modeling the brittle fracture behavior of concrete. Moving on to case study B, which is a modal analysis. Case study B1 and B2, the only difference being that case B1 incorporates a foundation with mass, while case B2 is a massless foundation. The outputs required the first 15 natural frequencies of the dam, the corresponding mass participation for each of these mode shapes, and the dam mode shapes for the first 5 natural frequencies were also required. Basically, modal analysis, it's quite a straightforward thing. It's just an eigenvalue analysis. So this is normally one of the first steps you would do if you were to do a dynamic analysis or specifically a seismic earthquake analysis. This gives you an indication of how the dam will respond under seismic loading in terms of what its natural frequencies are and the mode shapes. You can then compare this to your frequency content of your acceleration input or your earthquake input, and you can get a good indication of the sort of excitation you'll get under seismic loading. You also need this to look at or to define your damping, to see where the mass participation is. For rally damping, go to some structural dynamics equations. The natural frequency is a function of your stiffness, square root of your stiffness of your mass. Here's just the eigenvalue function, lambda, to solve your eigenvalues, basically your different mode shapes and your frequencies as indicated here. So what's important here is that when doing the modal analysis, you need to model the dam foundation and the reservoir, because under seismic excitation, the whole dam foundation reservoir acts as a coupled structural system, and they will interact with each other. There's various techniques to actually model your fluid structure interaction. Different softwares use different approaches. As you can see, this table summarizes the software codes as well as the fluid structure interaction approach and the fluid type used by the various participants, contributors, P1 to P13. Again, Abacus, ANSYS, Code Aster, all the well-known softwares are there. The fluid structure interaction, a lot of people still like to use Vestergaard added mass. Obviously, there's pros and cons for that. You can use acoustic mechanical coupling. You can model the actual reservoir as a fluid body, or you could use sort of acoustic elements. Depends on what's available in your software. And the fluid type can be modeled as incompressible or compressible. So for Vestergaard added mass, basically you're actually just adding mass to the structure, so you're not actually getting a stiffness effect. When you model your reservoir, it sees the reservoir as incompressible, and it's just like sticking the reservoir to the upstream face of the dam and providing an additional mass to the structure. So theoretically speaking, acoustic or fluid elements are more, how do I say, mathematically correct, but it has shown that Vestergaard added mass generally also gives good results. The results for the modal analysis, natural frequency results comparison. This is again case B1, which is a mass foundation. You can see first 15 modes, all contributors, and the contributors with advanced FS fluid structure interaction and contributors with Vestergaard added mass. So the organizers actually split them, knowing that you'll get significant differences. Let's just look at the first mode. All the contributors, the mean natural frequency is 1.76, the median 1.85, and a standard deviation of 0.36. contributors using Vestergaard added mass have a marginally lower natural frequency. This is because there's more mass, as I said, whereas yeah, for fluid structure interaction, the natural frequency is marginally higher than Vestergaard added mass. Some of the images just showing some of the outputs of the mode shapes for the dam. Frequency is 1.9 hertz, 2.2, 3.3, 2.7. So it's mode shape 1, 2, 3, 4. And this bar graph actually showing a direct comparison of the first 6 modes of the various contributors. You can see again there's a good correlation between the natural frequencies. For mode 1, these contributors had close to 2 hertz. These contributors were quite similar. And apart from contributor 13, the black bar chart, which actually shows significantly lower natural frequencies than all the other contributors. In this plot, I'm just showing you basically the various mode shapes that were actually output by the software. Well, sorry, the first mode shape by the various software programs for Mass Foundation. You can see generally there's a good correlation between the mode, anti-symmetrical mode, where the arch displaces towards the upstream and the downstream on either side of the spillway. The natural frequency results comparison for case B2, which is now Masses Foundation. You can see that there's a slightly better correlation, although for some reason contributor 13 has higher frequencies for all of the 6 modes. Looking at mode shape 1, you can see again the difference between the contributors with Vestergaard added mass and those who use fluid structure interaction. The first mode shapes derived by each of the 11 contributors for the Masses Foundation. You can see it's very similar as to the Mass Foundation, although the frequencies are marginally higher because with the Mass Foundation you've got a lot of mass, inertia mass in the foundation, which lowers your frequencies. So basically going to the findings for case B, generally good agreement between contributors except for participant 13. Vestergaard added masses generally give lower natural frequencies than the fluid structure acoustic elements. The Mass Foundation approach, okay, generally lower natural frequency, I've already said that. There's better agreement in the modal frequencies using a Masses Foundation. All contributors show first mode shape being antisymmetric. This actually correlates very well with research done by Dr. Nyoni at UCT for a medium thick wide valley U-shaped arch dam. Dr. Nyoni and Prof. Moyo at UCT have done some extensive studies on mode shapes of arch dams in relation to the valley, the width of the valley and the thickness of the dam, and whether it's double or single curvature arch dams. Here you can see for a double curvature arch dam with a medium thick arch, the first mode is normally antisymmetric, which correlates well with what was done here, which was shown at the workshop. So you can see that what we're doing here in South Africa, yeah, ties up very well to what the guys again are doing at the benchmark workshop. Here's just an excerpt screenshot taken from a table for Dr. Nyoni's PhD thesis, where again he shows all the various mode shapes. Well, for the first 10 modes, he shows mode shapes for single curvature, double curvature, arch dams, thin arch, medium, thick, and thick arches. So it's always a nice verification to do when you do a modal analysis to check that. Case C, case study C, foundation dynamic analysis. The objective and goal to verify that under free field foundation modeling conditions, the seismic motion is accurately reproduced at the free surface. The accuracy of the deconvolution of the earthquake for application at the foundation base. Evaluate the effectiveness and suitability of free field boundary conditions, non-reflective or absorbent boundary conditions, and comparisons of various approaches for contributors. by contributors. So basically, in order to do a seismic analysis of a dam correctly using the mass foundation approach, you need to ensure that the seismic input that is applied at the base of the foundation is actually deconvolved so that when it propagates up through the foundation to the surface of the foundation, that it actually represents the surface signal. So basically, when you do a seismic analysis, you take acceleration signals that were recorded at free surface conditions. So there's a famous earthquake somewhere in California. They recorded it at surface. But now you want to apply that surface condition, that surface input at the base, and then it amplifies as it goes to the top. So you need to actually do a reverse engineering method called deconvolution, where you actually reduce the amplification of surface signal so that if you place it at the base and it propagates towards the free surface, you actually get the original earthquake signal. This is it can be quite a complex and laborsome task, especially in 2D and 3D. But basically, it's important to see how the various contributors and how various people do the deconvolution. On this image on the right-hand side, just showing your typical free field boundary conditions. KC foundation dynamic analysis. Basically, on the table on the left-hand side is a summary, again, of the various contributors and their seismic inputs, how they deconvolve the signal, what did they use, what software, what approach. A lot of people, I know Deep Soil is quite a well-known software. People use Shake. Some of them do it in the finite element program. Also non-reflecting boundary conditions. How do the various contributors model the extents of the foundation so that they don't get reflection of the acceleration off the boundaries? So basically absorbent boundaries or non-reflective boundaries, as well as sometimes dashpots can be used. Perfectly matched layers. So there's quite a few various techniques that people use to actually model the free field conditions for seismic analysis. Model assumptions. So as I said, it's the finite element model of the foundation only, linear elastic material properties, the mass foundation, 0% viscous damping, absorbent, non-reflective, compliant boundary conditions, no static load, only earthquake. The earthquake acceleration signal, 3-component, in-stream, cross-stream, and vertical. And here you can see the various acceleration seismic input signals, the in-stream, cross-stream, and vertical. This was taken from a Bulgarian earthquake event with a return period of 1,000 years and a probability of exceedance of 85%. So the required analysis results were to extract the acceleration response in the FE model at the surface of the foundation, halfway between the crest of the right bank and the outer extent. So basically, you'll apply your earthquake signals at the base and let them propagate up, and you extract the accelerations at this point over here. And those extracted earthquakes need to represent the actual measured earthquake under free field conditions. Here you can see the various response spectrums for the in-stream, cross-stream, and vertical acceleration inputs. The results, there's a reasonable correlation between the response spectra produced by the contributors, except for P3, which is the orange curve over here. So here you've got the in-stream. Okay, sorry, this is the response spectra curves of the output acceleration extracted at the surface. So you can see in the response spectra, all of the curves sort of follow a very similar form, except some of them have higher peaks and more amplification, except for participant 3, which is notably different. The best fit was provided by participant 7, contributor 7, and all the results are deemed acceptable for conventional engineering design purposes. You can see the input represented by the dashed green line. It's quite hard to see because all the lines are on top of each other, but that dashed green line goes somewhere along here, and that is basically your target response spectra from the original free ground surface signal, and these are the extracted response spectrum from the various contributors. And in most instances, you can see it's marginally conservative. That's why I say it's acceptable for conventional engineering purposes, but most of them err on the conservative side. Case study D, which is now a linear dynamic analysis of the dam and the foundation. So basically the inputs are the same. You've got the same seismic inputs, which you apply at the base of the foundation. You need to apply your deconvolve signal, which you would have derived in case C. The objective and goal is to investigate wave propagation phenomena within a three-dimensional structural domain, particular attention given to the effects introduced by a canyon-shaped foundation. Observe and compare amplification of acceleration at the crest of the dam in comparison to free field earthquake signal. Comparison of the various approaches by the contributors. And you can see large amplifications can occur, as presented in the paper in 2023 in SANCOLD. You can have amplifications up the dam from the base towards the crest of to a factor of 10. This has been recorded before on site at certain dams. So the model analysis assumptions: linear elastic again, reservoir, same reservoir, full supply level, static and dynamic loading. For dynamic loading, include the dam foundation and reservoir mass. That's the mass foundation. Damping 5% for the dam, and apply suitable mass foundation boundaries and adopt earthquake signals as being free field. Again, the three input acceleration signals, which were measured at free surface. I'm not going to go too much in that again. The required results from the contributors: acceleration time history outputs at the crest level of the central cantilever in terms of a response spectra curve. The minimum and maximum dynamic displacements, minimum maximum hoop stresses, minimum maximum vertical stresses of the central cantilever, and contour plots of envelopes of maximum minimum principal stresses. For various contributors, again, these are just showing the assumptions they use in terms of the fluid structure interaction approach, the fluid type, also the integration scheme for the solver, implicit or explicit, and the various software codes. Looking at the results in the plot below, the response spectra plot showing the response spectra of the dam at crest level, and you can see there's quite a large range of acceleration, even at period 0, which is your PGA. Contributors 3, 4, 8, and 12 report values in the range of 10 meters per second squared. Others 15, 20, 30, whilst the input maximum acceleration is 2.5. So you can see that from the base of the dam to the crest, you can actually get amplification from 2 to 10 times. This shows that there's quite a broad distribution between results because of the complexity in the various inputs, the loading, the seismic loading, the deconvolution, the various methods and approaches used for modeling the fluid structure interaction, for modeling the non-reflective boundaries. So there is quite a broad spread in results. There is correlation as well. The contributors all reproduce resonance peaks at 0.06, 0.12, and 0.22 seconds. The amplitudes of the peaks and the shapes of the spectra are not necessarily well comparable. Having a look at the radial displacements, these are envelopes of the maximum dynamic displacement results versus elevation of the central cantilever. The displacements are taken relative to the base of the dam. Because it's a mass foundation, you will have displacements in the foundation, but in the lower portions of the foundation, but the base of the dam, being the top of the foundation, is taken as the reference point. Most contributors show very similar trends in the max and minimum displacement. Obviously, this time you've got positive displacements on the right-hand side towards the downstream, and you get negative displacements towards the upstream because under seismic loading, the dam actually oscillates between upstream and downstream. Again, you can see contributor 3 has quite a difference compared to the others. Even contributor 8, the dark green curve, differing quite a bit from the rest of the group. Otherwise, you can see quite a relatively tight agreement between the maximum radial displacement. Hoop stresses on the upstream face, negative stresses again denoting compressions, and positive stresses tensions. These are envelopes of the hoop stresses. Again, you can see there's quite a good correlation between most contributors, apart from 1 or 2, the orange and the blue curves. And on the right-hand side, the hoop stresses maximum envelope, those are actually your tensions. So that would result in an opening of the joints if you were to model nonlinear material models, nonlinear material modeling at the joints. Hoop stresses on the downstream face, envelopes of minimum maximum hoop stress results versus elevation of dam. It's a pretty similar thing. I'm not going to repeat myself. Vertical stresses on the upstream face. It's interesting to see here with the vertical stresses, there's a significant difference between contributors. Well, generally there's a good agreement, but it seems to be a little bit broader than before. This is again due to the complexities of different ways of doing seismic modeling, but generally there's still a good agreement. Vertical stresses on the downstream face, range of minimum at the base to -3 MPa, -8 MPa, which is compression. Looking at the major principal stress plots of the various contributors, tensile stresses develop at the upper half of the dam with peaks in the blocks towards the banks just below the spillway. So for instance, in this plot, you can see tensions developing on the right bank, on the downstream face, and on the left bank. And similarly, most of the other plots indicating the same pattern. Case study E, which was now a nonlinear dynamic analysis. So again, all the assumptions and parameters are the same as case D, except that case E1 and case E2 adopt nonlinear interfaces at the contraction joints, as well as E2 at the contraction joints, as well as dam foundation interface and dam concrete. To give an overall representation of the major principal stresses, you can see similar stress patterns, but you can clearly see discontinuities between the contours between the dam blocks, obviously due to a stress redistribution there. So where there's tensions, these contraction joints actually open during the seismic event and allow for redistribution of tensions. For the interface stresses, here I've got some plots from the contributor showing the normal stresses that occur at the interfaces. Here you can see tensions at the heel of the dam. Over here you can also see red showing tensions at the heel, and portions of red at the contraction joints, obviously showing that there would be some opening of the joints towards the crest under the seismic loading. Case E2, using a nonlinear material model for the actual concrete. All the result plots from the various contributors showing potential fracture damage occurring on the right bank on the downstream face in that region over there. So there's a bit of similarity as well. But again, now we're going to very complex analyses where your results start to differ due to different approaches. Case F, which is your massless, which is the same as case D, seismic analysis of the dam and foundation, but now you're assuming non-linear, sorry, not non-linear, you're assuming massless foundation. So basically, no need for free field boundary conditions. Displacement, acceleration, stress response of the dam is generally more conservative. When you do massless foundation, you generally experience no radiation damping. The foundation is modeled only in terms of its stiffness and not mass, disregarding inertial effects of the foundation. All the kinetic energy in the system is applied at the foundation extents is basically transferred directly to the dam base, which is unrealistic, because in real life you'll actually have a coupled system between the dam foundation reservoir acting structurally together, and the dam and the foundation directly influence each other, creating energy waves that travel through the soil away from the dam. So there's always the age-old debate between numerical modelers between mass and massless foundation. Massless foundation has stiffness but no mass, no inertia in the foundation, no energy storage or dissipation in the foundation mass, no wave propagation. The input is pretty much imposed directly on the base of the dam, whereas in a mass foundation, the foundation has a stiffness and a mass. The foundation participates in the vibration and excitation. Some of the energy is stored or dissipated in the foundation mass, and radiation damping occurs, and the foundation moves with the dam. So, as I said, it moves as a coupled system, so you don't just have the case of this dam jumping around on the foundation. The dam and the foundation sort of jump together, so there's a certain sense of agreement in the way that they get excited. For the results for case F, the average of all the contributors or comparison of mass versus massless foundation. So basically the organizers just averaged the displacements for mass foundation and massless foundation, case D1 being mass foundation, case F1 being massless. As you can see, the radial displacements, the light blue and the dark blue, massless foundation both showing higher displacements. Similarly for the hoop stress and the vertical stresses, again, the massless foundation results in the development of higher hoop stresses and also higher vertical stresses. So you can definitely say in this instance the massless foundation is more conservative, which is most of the time the case. So for theme A, what are the lessons learned? The finite element modeling is a tool to assist with analysis and design. It should not be trusted blindly. The benchmark workshop showed us that 12 expert engineers around the world with many years of experience undertaking to solve the same problem may still produce different solutions. So even the experts differ. Their results, the FE analysis results are sensitive to what may seem like small modeling errors or input assumptions. Linear elastic analysis approach should always be adopted prior to nonlinear analysis. Be wary of inherent numerical modeling anomalies or artifacts. Different numerical modeling software packages may produce different analysis results, even if the modeling inputs are identical. Effective numerical modeling is to some extent an art form that is learned with much experience. As you learn how to deal with it and understanding these modeling artifacts. So that's the end of my unpacking and discussion of theme A. As I said, I won't have time to do theme B and theme C, but the proceedings are available. I just want to have a look at one or two other things. As part of the benchmark workshop, there was a site visit to the SANCOLD Dam, a technical tour, just some photographs on the left-hand side being briefed. Yeah, I didn't make the site visit, unfortunately. I left at the end of the conference. I had some other appointments, but in the center there, the guys in the dam gallery, and on the right-hand side, a photo taken of some of the participants on the crest of the dam. Also, the participants were taken into the powerhouse, and they were also given a chance to look at the dam surveillance monitoring data and system, which was all quite interesting, I'm sure. Okay, I've got 10 minutes left to my presentation. As I said, there's an extra bonus. At the benchmark workshop, there was a paper that was published and produced or written by two esteemed gentlemen known as Emmanuel Robbie and Jerzy Solomon. This paper was written on the ADSYS software. So ADSYS is the Arch Dam Structural Analysis System. ADSYS is a numerical modeling program which was developed in the 1960s for analysis of arch dams based on the trial load method. Recently, Mr. Robbie and Mr. Solomon actually released an updated version of ADSYS 2024 using the original Fortran code and an updated GUI. Mr. Robbie, as I said, Mr. Robbie and Solomon are Technical Committee A members. The cool thing is, or what I think is nice, why I say it's a bonus, is that the software is open source software. It's freely available and recently made compatible with Windows. So I've actually put a link here for the download of the software for all of those engineers out there who would like to do structural analysis of arch dams for information purposes, or if you, I know sometimes the modeling software can be quite expensive and it's not always available to all engineers, but this ADSYS tool is very useful to get a feeling for the analysis of concrete arch dams. As I said, it was originally developed by the USBL in the 1960s. It was run on a Cyber 707428 computer, requiring 39,000 cards and 240 subroutines. What's interesting is in the 1950s, a single trial load analysis could take from 6 to 12 months to do by hand for a single experienced engineer. In the 1960s, ADSYS allowed various proposed arch configurations to be analyzed in a matter of minutes. So you can see drastically reducing the analysis time. ADSYS was used to design numerous notable historical USA arch dams. So it has been tried and tested. So for those of you who want to use it for a dam safety evaluation of an arch dam, if you don't have the correct FEA software, I'd really propose looking into this. It can be seen as the sort of arch dam equivalent of CADAM, which I know many dam engineers use for stability analysis of concrete dams, concrete gravity dams. Some interesting information. Morrow Point Dam, which is a arch dam in America, took 20 iterations to finalize the arch configuration. So imagine if each of those 60 iterations took 6 months, you'd be busy for 30 years. So having the software drastically improved the efficiency of arch dam design in that era. As I say, ADSYS was used for some existing dams in America. ADSYS has also been verified against modern-day FEA software in the paper published as part of these proceedings. They actually do some comparisons between the results from some of the FEA software. Typical analysis outputs principal stress vectors, your compression, your minor principal stress vectors, and your major principal stress vectors. You also get displacement results over here, shown in this image, as well as a breakdown of the moments along the cantilever and the arch elements. So you can get quite nice results from this analysis package. Then finally, I also one of the things that I came to know of from being part of the workshop is that there is actually an open source free advanced numerical analysis FEM software package. It's called Code Aster, and it was developed by EDF, which are a French company, dam engineering company. It was developed in-house by them. The software was actually used by contributor P5 in the Benchmark workshop, and the results correlated very well with all the other state-of-the-art software, such as Abacus and ANSYS. The software has very little limitations, very powerful and capable of advanced numerical analysis. Thermal, seismic, eigenvalue, static, nonlinear, fluid elements, FSI, free field, all of those. There's one small drawback. It's not very beginner friendly. I mean, but that goes to say for any FEA package. This one uses command files usually instead of a GUI, but I believe there is a GUI that has recently been released called Salome Mecca. I've again put the link for download over here. So if there are any dam engineers who have a complex dam problems and they want to give this a try, I think they should definitely look into that. Yeah, so you can see as the field is advancing, there are people releasing open source FEA software, which is available to everyone. So you don't need to have expensive software packages. In conclusion, the ICOL TCA benchmark workshop was held in Sofia, Bulgaria in 2025. 3 themes were studied. Theme A, an FEA analysis of an arch dam. Theme B and C, embankment and CFRD dams. All the contributors and participants shared knowledge and advice and tips on numerical analysis of dams. The proceedings were published and are freely available as open source literature. The benchmark proceedings serve as valuable analysis reference for beginners to test their ability. I think this is very important. It gives you a lot of confidence in your results. If you want to start getting into numerical modeling, you can practice by using even the inputs that they provide in the benchmark analysis, and you can compare your analysis results. There is powerful and verified open source FEM software available, and never blindly trust numerical modeling results. I just want to say thank you to ICOL TCA for hosting the event. Thanks to SANCOLD for allowing me to represent South Africa at the 2025 Benchmark Workshop Conference as a TCA member. Thanks to ARQ Dance for financing my trip to the workshop. Thanks to Bunkold and the workshop organizers for an insightful, enjoyable workshop. And thanks to Sophia for the sites, the culture, and the food. Thank you, Ashley. That pretty much concludes my presentation for now.
Thank you, Ryan. I really appreciate the time and effort that you put in to come and speak to us today. I would just like to start with a disclaimer that this session is being recorded. And the recording will be made available to everyone afterwards. I would just like to open the floor to some questions. If you have a question, please raise your hand, or else you can ask your question in the chat box and I will read it to Ryan. Okay, Alan, I have activated your mic. You can unmute yourself and ask your question.
Thanks, Ashley, and thanks, Ryan. That was an excellent presentation. A quick one. Our old, all our arch dams are old, except for Kotsi Dam in Lesotho. And as you know, and you've presented many papers, on many of the Department of Water and Sanitation's arch dams, and on other one, ambient vibration monitoring is used to supplement numerical analyses, yours as well. Just a quick one, was this mentioned or discussed at the benchmark workshop? Is it used elsewhere? Because as I say, our dams aren't old, they are very old. Many are some are more than 190, 100 years old. Kotsi, much newer. So we haven't got pristine dams. Pristine meaning brand new, and you'll have weak joints or they're cracked in places, sometimes diagonally, etc., etc. Please just give us a general comment.
Hi, Ellen. Hope you're doing well. Thanks
very much.
Thanks for the comment, and thanks for the question. So yes, interestingly enough, there are other engineering firms or dam engineers out there who do use ambient vibration monitoring. The ambient vibration monitoring was not included in this particular benchmark workshop as a requirement. But when one or two of the contributors, as I specifically remember EDF, the French, when they actually presented their findings, they said that they normally, as a standard procedure, always do some form of calibration through ambient vibration monitoring. So there are other people in Europe, I know the French do it, I think maybe the Italians, but there are a few engineers in Europe who do it. I have heard of engineers in the USA doing it. So it is a relatively new technology, and some people are for it and some aren't. But yes, it's definitely not just done in South Africa. And it's interesting to see the guys, the French, do it as a standard procedure. So every time they evaluate a dam, they start off by looking at the initial design or analysis parameters, and then they calibrate that by doing ambient vibration testing, and then do they actually only do the dam evaluation on a calibrated model.
Thanks very much. Thanks a lot.
You're welcome.
Thank you, Alan. Are there any other questions? I don't see any in the chat. Does anyone want to raise their hand?
I hope it wasn't so boring that no one even cares.
No, I don't think it's that. I think they just
Ryan, it wasn't
you
that.
covered everything.
I had to ask the question because we just do AVM generally in South Africa, or seem to.
Yes, no, it's a good question, Alan. Thank you. It's a very good question.
Okay, and then, so since there are no further questions, something might have come up in the chat. Okay. We have a question that asks, why did they not consider temperature load in the analysis?
That's a good question. So temperature, look, the purpose of a benchmark analysis is not to do a full design suite of analysis. We're not checking the safety of the dam. We're taking a dam, an existing dam where a design was done, analysis were done, and we're selecting certain analyses to do, and we're comparing them. I think if all the different loading conditions needed to be considered, it would make it a very lengthy process. But some of the previous benchmark workshops did actually look at thermal loading as well. I think there was a benchmark done on some of the Swiss arch dams where they definitely did include thermal loading on the dams. So not particularly in this benchmark, but each benchmark they select a few different loading cases which they think are relevant at the time and that they're interested in, and it's up to the formulators to really decide. But yeah, if you're particularly looking, sorry, I don't know who asked the question, but if you're looking to calibrate some of your thermal studies, there are definitely benchmark workshops where they have done thermal studies. And I've actually spoken to the guys from the technical committee, and they said they're happy for me to share the proceedings from the previous benchmark proceedings as well with members of SANCOLD. So if your firm is a member of SANCOLD, then I'm able to share this with you. So if you want to look at some thermal benchmark studies, I can gladly help you with that.
Thank you.
Cool.
Okay. We have another question. It probably takes a bit of time to type. Is free vibration analysis required for the arch dam, and is there any input parameters dependent on this natural time period of dam?
Okay, thanks for that question. So free vibration analysis, I'm assuming you mean ambient vibration testing. I'm assuming you mean doing a free vibration analysis of the actual dam on site. So basically that is pretty much linking up to what Alan asked. So basically a free vibration analysis can be done theoretically. So you can model the dam in your FEM software and do an eigenvalue analysis, and you can extract mode shapes and frequencies. And these are based on your dynamic characteristics, so your stiffness, your mass, your geometric configuration. You can calibrate that by doing a free vibration analysis of the actual dam, where you put accelerometers on the dam and you measure the vibration of the dam under ambient conditions. So the ambient conditions would be wind loads, chop from the reservoir. Any structure that you see in real life is always under some sort of vibration. You can't necessarily see it. It's very small, but you can have vibrations in the order of 10 to the minus 6 Gs, and you can actually measure that if you have a very sensitive accelerometer. So ambient vibration monitoring does that, where you place a bunch of these very sensitive accelerometers on the dam body, and you can actually measure how the dam is vibrating. So under ambient conditions, there's a whole broad range of vibrations going on at a whole range of different frequencies, but obviously the natural frequency of the dam will pick up and will be amplified according to what the frequency content of the structure is. Sorry, the resonant frequency of the structure. So it's not required to answer your question directly. There's no specified criteria or anything, but if you want to give yourself confidence in your analysis, especially with an existing dam, like Alan said, an old dam, 50, 60 years old, I think it's not necessarily correct to assume the same concrete and foundation parameters as were adopted at the initial design stage. Over many years, the concrete can age, degrade, various things can happen, and the stiffness of the concrete can actually reduce, or sometimes it can even increase. There's various things that can happen. So you never want to base your analysis of an existing dam on the original design material. You want to try and get the actual parameters of the dam as it is on site in situ at the moment. And that's what you do, why you do vibration monitoring.
Right. Thank you so much. Unfortunately, our time is up, so I'm going to end the presentation here. I just want to take 1 minute. Ryan, if you want to answer that question, maybe you can answer it in the chat a little
Sure.
bit later. And then I would just like to take 30 seconds to say thank you so much, Ryan.